Hey, it's Camilescu and welcome to part 3 of making of a DJ mixer. In this part we'll talk about the circuitry, so we'll talk about electronic schematics and dive deeper into my mixer circuitry and UREI 1620 circuitry. But before we do it, I want to sum up what we've done before. So on the first part of this series, we're talking about skills needed to build a DJ mixer. So in general, we talked about what we need to know to do it and what resources can we use to educate ourselves on this topic. So I recommend watching the previous parts before watching this video. On second part, we were talking about the first skill. We were using the first skill that is needed to build a DJ mixer. We were talking about block diagram, so this needed understanding of audio signal processing to talk about this concept. We talked about block diagram of UREI 1620 on part 2, and we talked about the separate modules that make this mixer work and make it complete. So in this episode we'll talk about the second skill. So this second skill is understanding electronic schematics, and I can't teach you electronics here. It's a kind of complicated matter, but don't worry. It's on this level we'll talk about electronics is not super complicated, but it requires some knowledge to gain some knowledge about understanding electronic schematics, I recommend going to university, but this is not super necessary. You can just read books and read some legit resources from internet. From my experience, I can definitely recommend 2 parts of Art of Electronics by Paul Horowitz and Winfield Hill. This is first part, this is second part. Those books are quite thick, and they talk about electronics using quite simple language. This book is very logically planned, so you first talk about general ideas and then dive deeper and deeper. And this book covers just most of the topics that you want to know about electronics, and this book covers analog design as well as digital design. So to understand what we do here, I think that we'll need like a quarter or half of this book. We'll not talk about digital signal processing, and we'll not cover all of the electronic circuits. So yes, you can understand how electronics work without university, but university will for sure make you dive really deep, and you can deal with professors that are really experienced, blah blah. But yes, reading books can be definitely enough, so don't worry. And there are some books that are written really well, so like by taking your time and doing it with care, you can understand electronics without school. So in our case, as I said, we won't talk about whole electronics. We'll talk about analog signal processing to make a DJ mixer, and there are 3 basic parts you must know to know what's going on here. So first part is a resistor. You must know what it does and how can you use it. Second part is a capacitor, and third very important part is op-amp. And op-amp is an integrated circuit mostly, because there are also some discrete op-amps. But op-amp is generally a complex device that consists of some transistors, some capacitors and resistors, but mostly transistors and semiconductors. As I mentioned, op-amps can be discrete, but most of them are IC. They're made with integrated circuit technology, And op-amps as a chip are in fact many transistors that are very, very tiny. When you say about op-amp, you say about this simple block with inverting, non-inverting inputs and output, but in fact this block consists of many transistors, and it's much more complex circuitry. But thank God, to make a DJ mixer, to make a basic DJ mixer, you don't need to really dive into op-amp construction and how they are made, and you don't have to understand those very complicated things that goes on inside op-amp. You can treat it just like this block, but when you are doing practical circuits, you must need you need to know something more about op-amps. You can't without brain treat it as a simple block. Op-amps can oscillate and generate signals we don't want. They can be unstable. So to achieve proper stability, you must know something more about op-amps. But op-amps used in audio are mostly very slow. For example, in UREI 1620 we will talk about, op-amps used are very slow and have quite low bandwidth, so they are not very likely to oscillate and cause problems. So it makes things much more simple. This is the end of this presentation. Now I want to show you the whole schematic of UREI 1620 and discuss all blocks, all circuits that makes this mixer. So I want to first show you that it's very simple to find original UREI schematic on the web. All you need to do is to type in Google UREI 1620 service manual, and voila. First position we have here is UREI 1620 manual. This is original UREI manual. It was made in 80s, and this is a very nice read. To know something more about this mixer and mixers in general, I recommend reading whole thing. But for now, I want to first come back for a second to block diagram, and then discuss separate circuits. So the block diagram is here, and we talked about this block diagram on a previous part. On part 2, on previous part of this series, with details, with some details, we discussed all the blocks that this mixer contains of. I must say that on previous episode I totally forgot about this stereo balance control, and I should have said about it because UREI has also this, but it's not very necessary to, like in my design there will be no stereo balance controls. So let's jump to first in this block diagram, let's jump to the very first thing that signal meets when entering this mixer. So when we deal with line signals, we transfer the signal straight to the source switch, that further the signal from the switch goes to the stereo balance control and then to level control. But on phono inputs we have phono preamps here. And this is the very first module I want to talk about. And we in this service manual we have a whole schematic of a phono preamplifier. And this phono preamplifier is not very common in DJ mixers. Most of the DJ mixers use active topology, and watching my classic Mixers Inside series, because I also made videos about some mixers on the market, I mostly say that phono preamps are active solution. They are single stage active, and what I mean by this, I say that to amplify the signal, because let's first very briefly say why do we need to amplify the signal from phono cartridge. We need to amplify the signal from phono cartridge, from turntable cartridge, for two reasons. First of all, a signal that is read by a needle from a vinyl record, this signal from a needle has very small level. Those are levels like 10 millivolts or something, and usually input sensitivity of mixers are in range of volts. So from those 10 millivolts we must amplify the signal to reach 1 or more volts. So first of all we need to amplify it, and the second reason we use phono preamplification is that the signal that is written on a vinyl record don't have flat frequency response. The signal that is the signal that is pressed to vinyl record has bass frequencies attenuated by 20 dB for 20 Hertz, and the high region, the high frequencies, are boosted for 20 kilohertz is 20 dB. So the frequency response is not even. And to reverse this, we need UREI equalization. So basically we need some kind of filtration. Thanks to parts like resistors and capacitors, we can filter out the frequencies. For example, in EQ circuits, when you boost the bass, when you attenuate the bass or highs, mids, all you do in analog circuitry is you change parameters of filters that are usually built with capacitors and resistors. So yes, let's get back to this phono preamplifier. As you see, it's kind of unusual because it uses two stages. In most phono preamps used in DJ mixers, there is only single stage, mainly op-amp stage, and this single stage uses active UREI filtration. Here, on second stage of this preamp, on feedback loop, we can see UREI filtration. This is filtration for mid and lower frequencies to achieve the proper UREI curve to make the signal from vinyl record linear, to make the frequency response linear. So this filter is active, but as I said before, this filter in this circuit treats mid and low frequencies, and in most of the preamps, in most of the UREI preamps and DJ mixers, all equalization, all frequency range is treated with filter in the feedback loop, so only one stage is used to do this. Here, the gain, the amplification, is split to two stages, and also UREI equalization is split to two blocks. So first the cartridge enters the input here. It sees 47K input impedance, and this is very important to have 47K in case of moving magnet cartridges, because cartridge is made out of coil and magnet. The phono cartridge works like this, that the needle moves when it reads the signal from the record, and this needle has magnet attached to it, and this magnet with the needle moves inside the coil. So the coil doesn't move, and the magnet is moving inside the coil, And this change of magnetical field inside the coil causes inducing the voltage. This is very smart. And that's why we say that cartridges are moving magnet or moving coil. In audiophile world, in hi-fi world, moving coil cartridges are recommended. They have some really nice advantages, but in DJ world, most of the cartridges, or I think all of the DJ cartridges sold, are moving magnet. Moving magnet because the magnet attached to the needle moves and the coil doesn't move, so moving magnet. And this cartridge can be represented by a circuit, and in this circuit there is resistance and inductance. The cartridge, phono cartridge, has its own inductance, and because of it has inductance, it requires a specific loading, because when the cartridge loading impedance is wrong, so this, as I said before, this R1 resistor here, it determines the input impedance. So we know that the coil interaction with this impedance, 47K, will be correct and will not cause much resonance. But here in this phono preamplifier, UREI 1620, we don't have a quite necessary element, because usually in phono stages we also see a capacitor that is parallel to this resistor. There is a very nice article I can recommend you. Let's search ESP. This is Elliott Sound Product pages. I recommended this site on the first part. Magnetic phono pickup cartridges. Very nice article by Rod Elliott. Here he simulated the response of cartridge loading. Let me zoom it. As you can see here, this is the circuit that represents the phono cartridge. So resistance and inductance, as I said before. Every cartridge, every moving magnet cartridge has significant inductance. And here is the loading. Here we have very nice info that this loading is cable plus preamp, because preamp may have its loading, but also signal when runs through cable is also sensitive to cable capacitance. So the cable, concentrical cable, RCA cable, also acts like a capacitor, so it also adds some capacitance. So here Rod Elliott in this article analyzed interaction, cartridge and load interaction. And as I said, here you have bare resistor, but mostly you add some capacitance. You may want to regulate it to achieve perfectly flat frequency. I'm sorry. To achieve perfectly flat frequency response. So here are the results of a simulation. So for 47K loading in parallel with 100 picofarads, in this case, we have perfectly flat frequency response. This is red curve. Don't forget that this simulation is for one type of cartridge only. So when you swap the cartridges, when you swap, for example, Shure M44 with some orthophone and other things, they act differently, so they are sensitive to other values of capacitance. They are sensitive for capacitance in general, but only with one value of loading capacitance, you'll achieve linear frequency response. So, as you can see, for 47K and 100 picofarads, you have flat frequency response, but when you add some capacitance, 47K and 500 picofarads, you have here a boost. This is a resonance. The coil from cartridge, the inductance, as well as loading, so resistance and capacitance, are causing some resonance. And here this resonance is in audible range, and notice that it's almost 5 dB boost between 10 and 20K. So you can definitely hear it. And this also makes me think about comparing the mixers using a turntable. It's very hard to compare two mixers using turntable because those mixers may have phonostages with different loading capacitance. So the biggest differences in sound can be caused not by sound character of the mixer, but by the resonance of the input impedance. So I saw a very old video on YouTube. It showed it was comparing some rotary mixers. I don't remember what exactly, but there was E&S, Bozak, and vinyl records were used for comparison, and you could clearly hear in some mixers this resonance. So this makes the comparison nonsense, because you are in fact comparing input capacitance of phonostages instead of mixers. So it's very hard to compare phonostages of mixers. And another thought I have about the phonocapacitance is that you want to take care of your cables run from the turntable. It's best to buy low capacitance cables to have to have less interaction with the cable, or to buy a cable with set capacitance that you know that, for example, when you some manufacturers of cables give you cable capacitance per meter. So, for example, when you have 50 picofarads per meter and you will use a meter cable, now you know that your cable has 50 picofarads, and then you can further play with input capacitance to achieve this response. In HiFi world, really a great care is taken to avoid those resonances and to set the capacitance. In DJ world, I don't see people caring about it. Maybe it's not a very significant problem, but it's nice to know about this. So yeah, I think I said enough about this single resistor. Then when we enter this phono stage, we see this R2 is current limiting resistor, and we enter first gain stage. This first gain stage is op-amp in non-inverting configuration. The input is, here we see this plus, so we see non-inverting input. So this is gain stage in non-inverting configuration. There is plenty of gain here. So after this stage, this signal gets amplified in linear fashion. All the frequencies are amplified on the same level. No matter low frequencies, mid frequencies, high, they all go the same level up. Then, after amplifying this on first stage, we see low-pass filter. This is a passive low-pass filter that is responsible for part of UREI equalization that is needed for reasons that I told you about before. So After this filter, high frequencies are attenuated, and the signal is partly EQ'd due to UREI curve. And then we enter second gain stage, but this gain stage doesn't amplify the signal in linear fashion. All kind of frequencies are boosted by various levels. Thanks to this, we can achieve second part of UREI filtering, and the filter, low-pass filter I described before, I called it passive because to filter the signal we needed only two passive elements, only resistor and capacitor. And here the filtering is active because the filter is placed in the feedback loop. The filter is placed in the feedback loop, and it's filtered in active way. That's why I called most of the phono stages in various mixers fully active solution, because in most cases there is a single stage and all the filtering, all the UREI filtering is here. And in UREI 1620, the UREI equalization is split to two parts. First high frequency part is passively treated, and the second part of UREI equalization is treated actively. Then we exit the stage through this large capacitor. Those capacitors are used for for AC coupling of stages to not allow DC signal to flow further. Only AC, no DC. Yeah, so basically this is what the phono stage looks like, and for me this phono stage is it has very advantages, because thanks to gain splitting to two stages has less gain because they add. So for each stage we need less gain, and when we need less gain we can apply stronger negative feedback, and thanks to stronger negative feedback we can correct the distortion better. So basically the specs of op-amp that has large gain are worse than specs of op-amp that has smaller gain, because more negative feedback is used and there is less distortion. So phono preamp in this topology give you less distortion, and also thanks to the UREI split to two stages, there might be some advantages, but this is a very advanced topic. Passive filtering versus active filtering is very, very interesting topic, but it requires a very deep knowledge about op-amp stability, phase issues, and generally how a feedback loop works and how it interacts with various components like resistors and capacitors, because filters cause some phase shifts, and it's very, very complicated, and it will take a lot of time to talk about it. There are some resources on this topic on the internet, this passive versus active filtering, but you won't find much information on the web about this. On internet forums, when discussing passive and active filtering, you can find some nice information, but also you can find a lot of false information. So be careful. So yeah, I covered the phono preamplifier in the first module. So now let's have a look what we have next. Next we have source switch. So this is just a passive element, like a switch that switches the signal. This is very obvious. We have stereo balance control, that is also very obvious, and then level controls. Let's look at it, how it looks like on the schematic. The schematic may seem to be complex, but when you split it to parts and modules, you'll quickly understand that it's very simple. So let's again have a look at schematic. The signal enters the mixer with the connectors, then it goes to phono preamps, then it has 100K loading impedance, the impedance is set, and then it goes to balance control or input level control, straight from the phono preamp, or in case of line inputs, the signal first goes to the switch. You can see here mechanical switch. Then it goes again to balance control and input level control. The input level is very simple. The input level control is very simple. It uses a single potentiometer. Here's the symbol of potentiometer. And it doesn't have any buffering. When you are more advanced in electronics, you can come back to my video, Rain MP 2016S video, where I really deeply describe the circuitry there. And there you can see buffering close to input level circuitry. Here it doesn't have any buffering. So it's very, very simple. It's just to control input level, to have channel volume control, you use only single potentiometer and nothing else. And from this potentiometer, without any buffering, the signal goes straight to the summing amp. Yes, the summing amp. There are endless questions about what makes summing good, what kind of circuits you want to use to achieve this famous glue, to make the tracks really glue nice together and work with each other. And it's very hard to answer this question. And there is one thing that doesn't help at all. I think that all of the DJ mixers use the same topology for summing. I didn't see any DJ mixer that use some exotic summing techniques. And here in UREI 1620, it's done with op-amps in inverting configuration. Op-amps in inverting configuration, this configuration is called virtual ground, because virtual ground, briefly, why? Because non-inverting input is attached to ground, and inverting input here, op-amps have some behaviors, and one of very important behavior of op-amp is that it always force voltages on non-inverting and inverting input to be the same. So here on inverting input we have so-called virtual ground, like 0 volts, virtual ground, because this input is forced to keep 0 volts on 0 volts level, because the non-inverting input is attached to ground. And this technique allows to make a summing amp. Here you can see summing resistors. This resistor, this resistor, this resistor, those are summing resistors that are connected with signal sources. Here, phono 1, phono 2, aux 1, aux 2. So via summing resistors, the signal enters the summing amp and the signal becomes summed with this very simple circuit. So after summing the signal, we have buffer amps here, and those buffer amps apply some gain to the signal, and that's why to keep 0 dB level on the most rotary mixers, for example in UREI 1620, but I think most of rotary mixer, to maintain a 0 dB level, you never twist the knob fully clockwise to the 10 position. You turn the knob to like 6 position, something like 1 or 2 o'clock. This is the position when you have 0 dB. When you further turn the knob, you take advantage of gain in summing amp. You boost the signal. So here this is a very interesting approach in UREI because mostly, as I said, the topology, active summing, virtual ground summing, is applied in, I think, all DJ mixers. All DJ mixers use this technique. What I observed in UREI 1620, what is unique, what is a standout, is that summing amp doesn't have any gain. It doesn't add any gain. The gain is 0 dB. And then there is buffer amp that is responsible for boosting the gain. In many DJ mixers, the summing amps are 2-in-1. They sum and they add gain. Here there are separate chips, separate stages to do summing and separate stage to boost the signal. And as you may notice, the summing amp has TL084 op-amp and the buffer amp has 5532 op-amp. I think that the reason of using 5533 amp here in this stage, the reason is that here the signal goes out to the effects loop. And 5532 op-amp can deliver more current, has more output current. So when you run some unknown devices in the effects loop, you will be more sure that you will drive them correctly, that you will have sufficient amount of current. It's more likely to happen when you use 5532 op-amp. TL084 may have, it will be risky to use TL084 in this application to effects out, because it doesn't have as much output current as 5532. So the effects loop is, as I said in the previous part, here the effects loop is very simple. It's just a break in the circuitry. You go out from the mixer with cables to effects, then you return the signal from effects with a cable back to the mixer, and you return to the input buffer. Here the input buffer is used because again, you don't want to use, because when you go back from the effect in the effects loop, this is also a known device, and you don't know how much current this effect will deliver. So, for example, you have some delay stomp box, yeah? You applied it to effects loop, and you don't know how much current, when the signal is sent back to the mixer, you don't know the current output capabilities of this stomp box. So to be fully sure that you drive the next stages properly, you want to use buffering. So here on the input of the mixer in effects loop, the first thing that the signal meets is input buffer. This is also a very interesting configuration, because it's not like first when you look at it, it doesn't make really sense, because here you have a voltage divider, so you attenuate the signal, and here there is a signal boost by 2 times. So first you divide the signal 2 times, you attenuate it, and then you boost it. This is not very optimal when you are considering signal-to-noise ratio, because attenuating and boosting the signal again doesn't make really sense, and makes the signal closer to noise floor, and then the signal is again attenuated with worse signal-to-noise ratio, because it was closer to noise floor before. So first, it may not make sense, but my theory why this input buffer works like this is that TL084 op-amp has limited common mode input voltage. This specific op-amp doesn't have unlimited common mode input voltage. It doesn't go to voltage rails. On negative rail is a bit limited, and non-inverting configuration makes it sensitive for input common mode voltage. So to avoid a large input common mode voltage, I think that they first attenuated the signal to be sure that the limit won't be exceeded, and then they again amplified the signal. So they made a sacrifice with worsening SNR a bit, but thanks to this sacrifice, you are sure that you won't exceed input common mode voltage. And in my circuit, even though it seemed that it doesn't make sense, and maybe I could think about maybe better buffering, I will copy this solution, because I want to be as faithful to the circuitry as possible. And then in original UREI from input buffer, the signal goes to tone controls. I said in original UREI because in my mixer there will be tone control for each channel. Here the tone control is in master circuitry only. In my case it will be for all the channels, also with the input buffer, and here we can see a classic Baxandal tone control. This is it's quite easy to understand, but it's a bit complicated to build your own Baxandal circuitry, but there are some very nice resources about it. You can read some things about Baxandal circuitry, for example in Small Signal Audio Design book by Douglas Self. So here you have this tone control, which allows you to cut and boost low and high frequencies with delicate cut and boost. You can do it by approximate you can attenuate the signal with 12 dB and boost it by 12 dB, more or less. So this is not very aggressive equalization. So here, this is classic Baxandal EQ circuit, and then from the EQs the signal goes to output amps. Here we have it. It goes via resistors straight to mono out. I'm sorry. Oh. It goes to mono out via resistors. The resistors from left and right channel is summed passively via two resistors, and it goes straight to mono out. But also it goes to output amps that apply extra voltage gain. Thanks to output amps, you can boost the signal even more. And it has a very simple principle. Here the signal from equalizer goes to the passive volume control, and then from the passive volume control it goes to the inverting gain stage and it reaches booth output. And there is also interesting thing here. I mentioned about it in the previous episode when I was talking about discrete circuitry. This is the only oh, here I have it. This is the only part of the main signal path that uses discrete circuitry. So let's have a look why. Again, signal from master equalizer goes straight to volume control, passive volume control, and it enters also amplifier in inverting configuration. But as you can see, this amplifier works together with a complementary transistor pair. It's called a composite configuration, and this composite configuration, the main principle is that the op-amp and output stage, discrete output stage, works with common feedback loop. This resistor, 56K, closes the feedback loop, but as you can see, the output is here, so it's the output of discrete output stage, and it goes back to inverting input. So the feedback loop has like closes with two parts, with op-amp part and discrete part. Why doing it? Why do you do it? You do it because discrete circuitry here, the transistors, can deliver much more output current than this op-amp. And thanks to this, you can drive an output transformer, because output transformer is a very difficult load. The loading is approximately like hundreds of ohms. It's not thousands of ohms, it's hundreds of ohms. And when you know Ohm law, you can conclude that using the same voltage but lower resistance, to drive lower resistance, you need more current. So without this discrete output stage, this op-amp alone will be unable to correctly drive the transformer, and not giving enough current will cause enormous amount of distortion that is not pleasant. You don't want to push the op-amp to limits. Here you help the op-amp with complementary output stage. This is class AB, this is not class A output stage, so this is class AB output stage that is driving output transformer. So as you can notice, there are two types of outputs in UREI. The first output, booth output, is driven with op-amps. There is no discrete circuitry. When you use booth outputs on UREI, from input to output, you don't have any discrete circuitry. Only ICs, only op-amps. Here, the circuitry on house output, so main output, is discrete, and also the output transformer is used to balance the signal, because as you can see here, the signal is single-ended on both output. You have this hot output here, and you have ground, so you have two output pins, and here the signal is balanced, so you have hot and cold outputs on two XLR pins, and also ground. And thanks to sending the balance signal, the signal is more immune to interference, But I don't want to dive into this topic because by typing benefits of balancing the signal or blah blah, you will find a lot of very useful informations, and I believe that there are also very interesting videos on YouTube about it. So also let's take a look because now we discussed the whole signal path of UREI 1620, looking at block diagram. We described phono circuit, then we described stereo balance controls, level controls is just passive potentiometers, nothing to really talk about. Then the summing amp, this inverting virtual ground topology, effects loop, then tone controls with the buffering circuit, and then from tone controls you have master level and booth level, output amps. That's all. But we didn't mention two things. We didn't mention the power supply. This is also a very important thing. And we also didn't mention the cueing system. How to hear the cueing, how to do the cueing and hear the signal on headphone amps. But before we jump to the power supply, let's talk about the cueing system because it's super simple. Here we have headphone amp that you plug to headphones, and all the cueing is done just by mechanical switching. Here this cue switch decides if you on headphones hear cue or master signal, this one, and here when you select the cue signal you can select the source. The disadvantage of this circuitry here in UREI 1620, some people say that it's a classic way and it's perfectly fine. For me, I'm more a modern DJ and I like two more things. I like to have cue master blend with potentiometer to not only select 100% cue signal, 100% master signal. I like to blend it to be more sure that the tracks really go well together. And also here, when choosing cue, you are allowed to hear only one cue signal at the time. I prefer to have more flexibility, and for example, I want to have possibility to choose two cue signals in one moment. This is, for example, used. This kind of cueing is very popular nowadays. It's used in Pioneer mixers, Allen and Heath mixers, and stuff like this. So this is something I will improve in my mixer design. In my mixer design, that is, the main circuitry is inspired by UREI 1620, and it will be faithful, but the headphone amplifier and whole cueing section will be more modern. Let's only take a look at headphone amp, how it looks like. And headphone amp looks the same as output amp that is driving transformer. Thanks to this circuitry that allows us to deliver more current, we are also able to drive headphones, give more power to headphones to hear them well. So this is very simple, and yeah, this is not very complicated. So let's take a look at the last thing, the power supply. The power supply in UREI is very simple, it's linear type. Here we can see mains input. In Europe it's between 200 to 220 volts. In States it's around 100 volts, and yeah, I don't have to explain it. We have just main signal that enters the transformer. The transformer steps down the voltage. The signal is still AC, it's alternating current, and here it enters a rectifying bridge that rectifies the signal and makes DC out of AC. I don't want to really dive into this topic because those are basics of electronics, and there are a lot of resources that explain this. And after signal after rectification enters linear regulators. Before linear regulators, it's smoothed with capacitors. It enters linear regulators, very popular 3-pin regulators used in most audio circuits on the world. They are not super high-end. Those are very, very basic and cheap regulators. And then we have some capacitors. Here is the let's say bulk capacitance. This is 10 microfarad capacitance, and here we have smaller capacitors to do various things, to filter out high frequencies, to better the stability of regulator loop. There are several reasons to use those small capacitors. The power supply in my design will be also different than in original UREI, because I want to make it more modern. I want to use DC-DC power supply. As I showed you in the original Mixersinside series, when I showed you many mixers inside. Most of them have DC-DC switching power supplies, and there are very nice benefits out of using those power supplies. You avoid mains hum, so you don't have any hum that is in audible range. Switching regulators have very high switching frequencies. They are hundreds of there are hundreds of thousands of hertz. So when you in linear power supply, you charge capacitor with 50 hertz or 60 hertz frequency. So this charging can cause audible hum, and 50 and 60 hertz are frequencies that we perfectly hear. I think that this problem is known for you, and you saw devices that go like boo, and this is just essentially mains hum. There are a lot of problems with mains hum, and DC-DC converters makes it easier, and just switch the voltages with much faster frequencies that are well below audible range. Also, modern DC-DC converters have very fast feedback loops, and when you design a DC-DC converter properly, you not only can achieve really low noise, and that is perfectly fine for audio circuits, but also you can achieve better transient response, because the loop is well controlled, and the transient response is nice. So regarding power supply, I want to go modern way. So I describe you the whole UREI 1620 circuitry. So I think that at this point I don't have to describe the circuitry of my mixer, because my mixer is just inspired by UREI, so you know well what's going on here. So guys, I think that this episode was quite deep and quite long. Thank you for taking your time and listening to it. I hope that it was clear. Sorry for not explaining all the matters, but I think that I have no way. I don't want those videos to have to be 2 hours long, and also I think that to understand basic electronic problems, there are much better resources than me. I will be happy to tell you more about mixer circuitry. I will be happy to tell you about analog signal processing in mixers use, but I don't want to be a guy that teaches you electronics, because there are much nicer resources on the internet. So again, thank you for taking your time. I hope that this video was clear enough for you to benefit out of it, and part 4 will appear in the future. Thank you and see you next time.